Hi everybody, Gérard Berry speaking about Hiphop.js, asynchronous reactive web programming. Our goal is to add more reactivity to JavaScript. Complex web phone applications deal with three quite different problems: data computations, asynchronous communication and data transmission, stateful reactions to events coming from various sources, and this is usually a source of difficulties. JavaScript is okay for 1 and 2, but only has a basic handling of 3 with yield, async, and await that do help, but are not enough for complex cases. Hop by Manuel Serrano improved 1 and 2 by multi-tier and direct HTML programming, which we will illustrate later. But synchronous languages have been developed specifically for 3, and Hiphop will reuse STRL, my language from the 1980s. What does synchrony in Hiphop mean? Synchrony means that for all non-delay statements, control transmission and signal-based communication are assumed to be instantaneous. In practice, synchronous will mean that things are all done in the same atomic reaction. And that will imply that a Hiphop reaction is deterministic even is concurrent, which is very different from asynchrony, of course. So Hiphop.js imports its temporal statements from STRL. The delays are the same as in JavaScript, they were all native in STRL. It imports commutative synchronous concurrency, which will greatly simplify programming, signal-based synchronous communication between concurrent parts, preemption structure that controls the lifetime of their body in a very fine way. And this will be central to reduce complexity in reactive programming. Abort, every, suspend, and so on. And a generalized escape mechanism compatible with concurrency, break with a label which is above a parallel, which makes sense in synchrony but not quite in asynchrony. For integration within JavaScript, we chose not to make a direct integration which would lose too much of the semantics of synchrony, and instead to do a DSL very well integrated into JavaScript. We now discuss a Hiphop example, the Lisinopril prescription app. It was given to us by Stephen Belknap from Northwestern University, Chicago. Many medical accidents are due to bad prescription following, that's what he told us, and he asked us whether we could develop an app to check validity of actions and record them during the whole cure. Here is the official Lisinopril prescription. It's a hypertension medicine. Take one tablet once daily with time window 8 p.m. to 11 p.m. and time wall 8 hours between doses, which means don't take a dose in less than 8 hours from the previous one. To a computer scientist, this looks quite incomplete and ambiguous. So I discussed with Stephen. What if 2 doses are taken in less than 8 hours? Well, that's real bad. What if a dose is taken out of window? That's not good, but not real bad. What if the dose is forgotten? Nothing is said about that. Well, yeah, dangerous is more than 24 hours. How should mistakes be detected? How is your user warned? He forgot about the window, forgot about the 8 hours, forgot about the 34 hours. Well, he will not be warned. What about expliciting a simple protocol to take the dose and a way to record all events during the cure by a web phone app, for example, or even an automated pillbox if needed? That would be great. Protocol plus traceability is a good idea. If you consider all situations that can occur over time, and all the warnings and errors you have to send to the user, you discover that such a specification becomes quite complex. To program it with JavaScript, you have no easy way. You have to allocate several interconnected state variables and event handlers, which makes the global application state and the action to perform when receiving an event hard to grasp. This leads to programs that are hard to make modular, to debug, to read once correctly written, and to maintain and modify. In the paper, we show this is even true for a much simpler login interface. In the sequel, we show that the aforementioned temporal programming primitives of Hiphop are what we need to make programming much more natural and behaviorally modular by making the temporal structure of the application directly visible in the program. We now describe the interface and full hip-hop code of our app. Here is its interface. First, you have a time display with a green background when in the 8 p.m., 11 p.m. window and orange otherwise. And two buttons, try and conf. Try means I want to give a dose and conf means I confirm I have given a dose. These buttons are smart. They can be disabled, gray, for try if previous dose is too close, and for confirm if try is not yet accepted. Or they can be red, for try if previous dose is too far, and for conf if confirmation is late. To finish the interface, there are two displays, one for the time of the last dose, and one for warning and errors may be associated with bells, and all events are logged in a file. Before describing the code, we have to explain what is a Hiphop.js synchronous signal, the basic communication unit between statements. A signal S, always written in blue in the rest of the talk, has two attributes broadcast within its scope. A Boolean present-absent status, unique in a reaction, an optional persistent value, also unique in each reaction. Within each reaction, independently, the status is absent by default. It is instead present by the environment if declared input, or explicitly in the program by an emit_s hiphop statement. It is read by the expression s.now in JavaScript expression, which are used in hiphop for all data computations and all tests. The value is of any data type, and unlike the status, it is persistent between reactions. It is set by the environment if the signal is declared input, or by emit_s of exp in the code, where exp is any JavaScript expression. It is read in expression by s.now_val. Here is the code for the SmartButton module for try and confirm buttons. A module is a basic unit in hiphop. It has an argument list, which is a variable d, which is a delay for alert. The other arguments being signals. Tick, which is used to ring errors and the bells. B, the button itself, and active and alert, which are outputs to color the button. We start with button active and button not in alert mode. So by emitting active true and alert false. And then we enter an abort statement. Abort is a preemption statement. That means it will execute its body until this body terminates or until b.now occurs, which means that you press the button. So the body is wait for the delay in the number of ticks, which will be maybe minutes, and then emit alert true at every tick. Notice that this behavior would be infinite if not killed by b. So preemption is absolutely fundamental to simplify programming. And then when this is over, when B is pressed, we reset the button to the normal state, false, false. We now turn to the Lisinopril module proper, starting with this interface. For try, we have one input, which is the button itself, and four outputs for the coloring and marking errors. For conf, the same, and then we have an output to deliver the dose and an output to record the dose. And the errors that say that it has been too long since last dose. Now let's look at the module body, the real meat of the module. It starts by declaring signals, minute and in-dose window, that will communicate between the clock and the rest of the module. Then it follows by a for par. We put two things in parallel, a clock and the real stuff. The clock here does update of the time, coloring the display, and emit minute and dose window for the rest of the program. The other branch is a loop, an infinite loop, which corresponds to the whole prescription that will be stopped only by stopping the machine. Inside you have a sequence between a group of two phases. Phase 1 is wait for try, phase 2 is wait for conf, and phase 3 is wait for 10 hours, during which you are not allowed to press try again. It's a sequence inside the fork, which starts by phase 1, waiting for try. We will see the code in the next slide. When you get try, you deliver the dose. and you start phase 2, waiting for conf and keep alerting if late, of course. And then you record the dose and you execute this break, but I will explain it a little later. Because in between, we have to notice that in phase 1, 2, we need to keep alarming if the delay of 34 hours since last dose is over. We need to do that during both phases. So we use synchronous concurrency to factor out this code for phase 1 and 2. So this code will be running from the beginning of phase 1 to the end of phase 2. It would be infinite. So how to stop it? By the break. We break instantaneously the fork par, killing the other parallel branch, which is in this case the second branch of the par, to go directly to phase 3, waiting for 10 hours to allow try again. Once phase 3 is finished, then we exit the loop and re-enter it again as before. So this temporal structure is made completely readable and obvious by the language itself, what it would be hidden in state variables in JavaScript or other classical languages. That's the main advantage of Hiphop for programming reactive behaviors. To finish the code, here is the full loop body. Phase 1, waiting for try, start by instantiating the SmartButton with the right parameters, and when try is pressed, limiting a delivered dose, and then a warning if the dose is not in the timing window. Phase 2 is similar, I won't detail it. The common phase, which is to error if too long wait since last dose, the 34 hours. So you wait for these 44 hours, and then you keep emitting, sustain this, keep emitting, no dose is too long error. Here is a simple Lisinopril simulation web interface described in Hop. It could be described in JavaScript as well. It is simpler than the one we gave in the pictures, just to illustrate what's happening. We declare a service, Lisinopril. Its first component is a reactive machine, which is the compiled code, basically, of the Lisinopril program, with attributes, the input and output signals, and the execution function. It returns a HTML page. HTML is just a normal function call with a different syntax in Hop. As an example, here is the try button code. It has a side which is only foreground color here, and an on-click function. The tilde form here is a multi-tier programming goodie of Hop. Evaluate the internal form into a JavaScript code that will be the current code. The m.react form triggers a reaction of m with try present when the try button expressed. The color form computes the foreground color according to the value of try active and try alert after the reactions. For the output signals, we just print their name if they are emitted. For this, we use a map over the list of their names and a div react that will print the name if the signal is emitted, which is detected by m of sig.now. This is all we need for this simple interface. The graphical interface described before is done in the same way. We now briefly turn to the formal semantics and implementation. So the semantics are bought directly from SRL and are completely formal. It's a semantic chain, in fact, going from behavioral rewriting semantics to a very operational constructive circuit semantics, which is systems of Boolean equations, a hardware circuit in software. The implementation is based on a constructive evaluation of Boolean equations. I won't define what constructive is here, but it's strongly related to constructive logic. It goes by a fine-grained macro-scheduling based on the formal circuit semantics, and it yields a constructive linear time evaluation of the equation. The generated code is in standard JavaScript. It is compatible with any other JavaScript code in any execution environment. Atomicity of JavaScript implies semantic correctness of the compiled code with respect to the synchrony hypothesis. Now about performance. Due to the compiling techniques, code size and execution time are mostly linear in source program size. There are square cases, but very artificial ones. We give the example of Skinny, a large hop-hop program for interactive music, where the audience uses smartphone to choose in real time pre-composed patterns that are dynamically assembled using a set of pre-composed dynamic constraints to ensure that what is placed remains consistent with the composer's musical intention. Skinny is developed by Bertrand Petit, a music composer and computer scientist. Skinny has been used in several concerts, and it has shown its ability to achieve a good balance between the determinism of composition and the non-determinism of audience-driven performance. It is a large and complex modular hip-hop program that deals with lots of events and situations. It uses heavily synchronous sequencing, concurrency, communication, and preemption that are very well adapted to this high-level orchestration problem. Skinny generates about 10,000 Boolean variables, leading to 1.5 megabytes of JavaScript runtime code, that with a reaction time of about 15 milliseconds, which is largely fast enough for real-time concerts. If needed, more efficient compiling and optimization techniques are available. To conclude, Hiphop.js simplifies reactive applications in JavaScript by importing concurrency, communication, and preemption constructs from strl. Hiphop.js is based on Hop, a multi-tier language that extends JavaScript, but its generated code can be used with JavaScript only. No need for Hop when you run compiled programs. Hop and Hiphop are available as open source software under GPL license. And thank you for your attention.